Hello, everybody. Dr. White here with a quick look at moment-generated functions for binomial random variables. We're actually going to start out with the moment-generating function for a Bernoulli, just for comparative purposes. We've done this before, but here's the PDF, the PMF of the random variable, and so the moment-generating function was chance of failure times e to the t 0 successes plus chance of success times e to the t times 1 success, and it came out to 1 minus p plus p times e to the t. Like to see how that goes if we try it for a binomial. Okay, so let's let x be binomial. In trials, chance p a success each time. And when we compute the moment-generating function, we're going to have to sum for all x's 0, 1, 2, 3 up to n, e to the tx times the f of x that we have derived. Okay. When we stare at this a bit, it kind of looks like some stuff out of the binomial theorem in a way. And what I'm going to do is algebraically gather a few things together until I'm actually looking at an application of the binomial theorem. So I'm first of all writing e to the tx as e to the t to the x, and by commutativity moving that around a bit. And then another application of a rule of exponents says that this quantity is going to have to be the two bases multiplied together to the x power. Okay. Now, at that point, we're exactly in the form for a binomial theorem. A plus b to the n is the sum of some index I going from 0 to n of n choose I, a to the n minus I, b to the I. And that's exactly what we're looking at here, but with the index being x instead of an I, which makes no difference. And the a is p e to the t, and the b is 1 minus p. So this is actually just the a plus b to the n. So check it out. The moment-generating function for a binomial is the moment-generating function for a Bernoulli raised to the nth power. Okay. Heading on to try to find the expected value and the variance of a binomial. We'll use the moment-generating function technique. We take the derivative of the moment-generating function. So by the power rule, that's n times this stuff to the n minus 1 times, says the chain rule, the derivative of that stuff inside the parentheses. Derivative of 1 minus p is nothing. Derivative of constant times e to the t is constant times e to the t. Plug in t equals 0. And we get all this, but 1 minus p plus p is just a 1, so we've got n times p as our expected value, which should totally make sense. If something has a p chance of success each time, you try it n times, then you'd expect to be successful n times p at the time. Like if the chance is 50%, then try it n times 50%. 50% of n is, half of the number of trials. It seems it fits intuition. Okay. Now, for the variance, we're going to want to get the second derivative at 0. So we need to get the second derivative. So we're going to take the derivative of this stuff. So we're going to end up using the product rule, because of this function of t times this function of t. So I'll let you fight through the details, like stop the screencast and see if you can find an expression for m double prime of t, and check yourself, see what the book got. But I'll just say that when you plug in 0, you get this. Okay. So the variance of x is that quantity minus the square of the mean. And if I multiply this stuff out, I've got n squared p squared minus np squared. And when I square out this, I've got n squared p squared. So there's a little bit of cancellation leaving me with just this plus np and this minus np squared here. And I can factor out an np. And think about what happened here. You know, if you're looking at a Bernoulli, you're really looking at a binomial random variable with one trial and chance of success p on that one trial, as opposed to a binomial that has the n independent trials. And look at the relationship between the expected values, multiply by n. Look at the relationship between the variances, multiply by n. Look at the relationship between the moment-generating functions raised to a power of n. There's no accident about this. We'll see more deeply why it is so in a later chapter. But as far as the multiplying by n is concerned, at least on expected value, this should not surprise you a bit when you think about the structure of a binomial random variable with n trials. You can actually write any binomial random variable as the sum, I goes from 1 to n, of xi, where each of those xi's is a Bernoulli random variable with chance of success p. And those xi's are independent of each other. Like, what do I mean by that? Like, say x is binomial with 3 trials, chance p is success. And for every I from 1 to 3, I is 1, 2, or 3, define xi to be 1 if you get a success on trial I, and 0 if you get a failure on trial I. So each of those xi's is a Bernoulli. They're independent of each other because the trials are independent of each other. And the random variable x is actually the same as the sum of x1, x2, and x3. Like, for example, suppose that in your 3 trials you got success, failure, failure. Then your x1 would have to be a 1, and your x2 and x3 would have to be a 0. And so look at how the sum of them works out. 1 plus 0 plus 0. Basically, the 1s go along, and they add up to the number of successes. So this is a way where the sum is functioning as a way to count the number of successes. So this is a really useful and important fact, and we'll see the like of it in other sections. Here we're learning a binomial is the sum of independent Bernoullis, and this seems to bring about a nice relationship between means and expected values for binomials versus means and expected values for Bernoullis. So just keep thinking about that. I think now we'll turn back. The next screencast, we'll turn back and look at, maybe another computational example involving binomial random variables, and we'll head into R for that. So see you later. Bye-bye.